Yes.
Welcome to our Bucky call for this weekend, February 28th, March 1st. Anne will not be with us. I haven't heard from Joe, but we are here ready to roll. So, Manu, how are you feeling, and what do you anticipate out of today's call?
I'm feeling good, just waking up and wow, ready to board the train. I see that essential is there. So we progress. Um, Lee, how do you feel? What do you expect?
I'm excited about tonight. I've been waiting all week for this. I am wanting to learn even more. I have no idea. I don't even remember what last Wednesday was about. Um, so I, you guys are going to have to wake up my mind in memory. I know Wednesday we talked about memory. My brain is not functioning properly on memory. Otherwise, I, Richard, how are you doing? And what would you like to get out of today?
Well, I'm feeling pretty good overall. I'm continuing to experiment with AI, augmented intelligence questions, and their responses, and it's really interesting right now. I'm asking it in relation to a couple of projects, but to interconnect Bohm's undivided wholeness, Fuller's minimum system structure and tensegrity, David Pete's Blackfoot physics, and Appella Colorado's worldwide um, Institute of or Worldwide Indigenous Science Network. And the answers are coming back in a very satisfactory way from my perspective in terms of how they're integrating the knowledge base that's provided by all of these different sort of contributors. So, and again, all of it in many respects starts to connect with our readings of Amy and other readings in the Trim Tab group and so forth. So I'm looking to get more and more out of the importance of the minimum whole system sort of structures and understanding Boehm's undivided wholeness in more detail and more depth. Fred, how are you feeling? What's your expectations for today?
Thank you, Richard. I'm feeling a little bit ambivalent here. I have divided focus. I have one part of my focus is on U.S. bombing yet another country, and then the Bucky call. So I have to make a choice which direction I'm going uh, to apply my focus on this call. So that's how I feel. And my expected takeaway. I've sent all of you a link to a wonderful video by Three Blue, One Brown about mostly about the geometry of multidimensional spaces, which is fascinating and really well done with nice graphic illustrations. And Joe replied to me and he sent me a 3-page PDF with really wonderful remarks because he says this links directly into his current work. I'm not exactly sure what his work is, but it's about um, the inner workings of AI and finding a way to discover how AI could work out its own awareness and consciousness, as far as I understood. which may be a little bit too narrow, and my understanding may be too narrow, and his job may be a lot wider than that. But he told me, he gave me a lot of insights in this video from his point of view, and that really enlarged my way of seeing it. So I feel really good about that. So if you get a chance to watch this video, it's quite entertaining. It's well done, and it explains very profound things with minimal mathematics. I mean, affordable mathematics, simple formulas and things that we've learned in high school and stuff like this. So it's really a good one. And my expectation, as always, is let's try to learn a little bit something. Steve, how are you feeling, and what is your desired takeaway today?
Well, thank you. I'm a little bit frustrated because I thought, well, I'm going to use my new computer tonight, and in doing so, I found myself I now completely screwed up. I had taken quite a bit of time and prepared an analysis of that icosahedron issue. If you'll recall, I argued that the icosahedron in Amy's book was not an icosahedron, and I had some pretty good arguments for that. I'm prepared to discuss that tonight a little bit. I'm looking for, I wonder if I found it. I'm looking for the PDF file that had multiple pages on it. Let me see if I can find it right this instant. But I would like to talk about that in a way that to prove that I was actually right. And by the way, I just found my PDF file. So I'm pretty good to share all that. So I could talk about that if you guys wanted to talk about that. And or we could just go into the reading of the book, and then we're going to be starting at page 246, or figure 14-4 is where we're going to be starting. But I'd really love to tell you about what I discovered about the icosahedron. Are you guys open for that? Oh, and one more thing. I've been complaining with myself because I have not been getting the AI summary of this meeting. And in my new computer, I was setting up Zoom, and I discovered that there's a button I have to click to say, send me a summary. So I now have clicked that button. So maybe that was my problem, is I just didn't express my choice. So I will be getting an AI summary of these meetings, and I'm going to include that along with the chat and the transcript and the video. And those will, all the documents will be in Google Doc. I'll have a Google Doc link, and all of them will be put into the YouTube. And the YouTube link and the Google Doc links will be on the weekly send that I send. So that should be pretty exciting. And if you guys are interested in that AI summary, that will be pretty cool. I have to get used to what my face looks like on this, on my camera here. So that's kind of weird. So if you guys are open for it, I'm going to show you what I talked about, what I've discovered about the icosahedron. Are you open for that?
Sure.
Okay, good. Manu, you good with that? Richard, you good with that? Lee, do I get a nod all the way around? Okay, good.
But you better not let us point out the fact that you're going to be wrong.
Yeah, listen. Actually, I found out that I'm absolutely right and I'm wrong. So I'm both right and wrong. And I'll tell you what that's about. Thank you. Here we go. I'm just going to share my screen because I don't know what I'm going to do next. But my big gripe was on this thing right here. This says an icosahedron. And I said, well, this is not an icosahedron because an icosahedron has an equator of triangles around it. And every vector, every vertex, and every side of the pentagon in an icosahedron opens to a triangle, and this has a pentagon next to a pentagon. And so I was convinced that this is not an icosahedron. And you know what? I finished the whole argument, got the whole thing done. I've got a great PDF file here that I'm going to show you where I've analyzed this whole thing. We're going to go through the whole deal. But I suddenly read the caption on the picture. It's not an icosahedron. It's the 6 great circles of the icosahedron. So, duh, I completely missed the point. But I think a lot of people mistook this for an icosahedron, and it's not an icosahedron. It's a representation of the 6 great circles. And the thing that's evident is that next to the pentagon, every vertex connects to a triangle, so there should be a line across here, not a pentagon. And this, of course, is a triangle. It's a side to a triangle. This vertex. So what I did was I took a look and analyzed this situation. I started with this guy here, which is a pattern for a icosahedron. And I took all of these guys up here and numbered them, triangle 1, 2, 3, 4, 5, and I made them the North Pole. And when I do that, triangle 1, 2, 3, 4, 5, of course, you'll notice here there's a triangle off of each side of this pentagon. See this now, this becomes the North Pole pentagon. 1, 2, 3, 4, 5 is the North Pole pentagon as seen from here. And from that pentagon, there's a triangle number 10, triangle 15, triangle 9, triangle 11, triangle 8, 13, 7, 12, 6, and 11, because the equator of this icosahedron is all triangles. And then south of all triangles, off of 11, 6, 12, 7, the vertex of 6, the side of 11, the side of 12, the vertex of 7, the side of 13, the vertex of 8, and so on, that connects to one side of the pentagon, which is the South Pole. So this proves that there are only triangles adjacent to the sides and the vertices of the icosahedron. And that once we set up, while there are pentagons everywhere on the icosahedron, once we set up a pole, the 180 degrees becomes the other pole. Those become the polar pentagons. Everything else is a triangle. And so then what I did was I said, okay, let's arbitrarily pick another pole. So I grabbed my icosahedron. I said, let's make this the North Pole. And let's make this then 180 degrees the South Pole. And there's the equator going around. And if you build this, here's the South Pole of the equator. And then what I did, now, any questions so far on the polarity of the icosahedron?
I have a,
Did I get it wrong in any way?
I think you did.
Okay, share with me
Yes.
how I got it wrong, Fred.
How do I show you something so you can take a picture?
I will stop sharing so you can show me something.
No, it's on paper. I just drew it. Hold on a second. I changed my camera.
I don't need to pin your frame. You're going to share your screen, right? Yeah, there you are.
No. I'm going to.
Oh, you're just going to share your desktop.
Yes.
All right, good. So I'm going to pin you there so I can take a screenshot of the big U. I now have the big U. And let me see. I don't know how to do.
Can you see that now? It's too small. Let me put it up to the camera. If you can take a screenshot, you can then share it.
Okay, I'm going to take a screenshot right.
Okay, this.
You want to hold it a little bit higher? Okay, good. Hang on.
A little bit what?
Hang on a second. Oh, well, you've just proved my point. Your thing proves my point. Go
Okay,
ahead.
maybe.
I've got it. I've got it here.
You
I'm
get
gonna
it?
say
Okay.
Fred's
Okay, please,
icosahedron.
Please share the screen now.
Okay, it says it's automatically shared to my, let me, hang on, I'm automatically, edit your screenshots, automatically save screenshots, or save to open folder. I'm gonna have it saved to my download folder. And downloads. Why aren't I getting this to go? Change, I see, okay, good. All right, downloads, there we go. select folder, ask to save edited screenshots, multiple windows, or okay, good. I think that's it. Now let me go find it, and I will go to my downloads folder and find. Oh my goodness. Let me see. Let's go to.
Did you save it?
Yeah, I thought I did. So hang on. Oh, no. See, this is the problem with a new computer. So I'm going to breathe deeply now. And let's see if I can just go to my computer and see if it's saved in screenshots before I got a chance to capture it. These personal. Pictures, screenshots. Got it. Here it comes. Okay. And I'm now going to share it and you can discuss it. Okay, good. Everybody should see that at this point.
Yeah, all right.
Okay, this proves my point.
Okay, can you explain to me how this proves your point?
Okay, well, here's your pentagon. This is a polar pentagon right here. By doing this, this pentagon becomes the North Pole. Adjacent to this side of the pentagon is a triangle. Adjacent to this vertex on the pentagon is a triangle. Adjacent to this side of the pentagon is a triangle. Adjacent to this vertex. Oh, no, this should be going across here. Yeah. May I show you my drawing? Because you should be drawing your line across here. It should not be there. So let's see if I can.
This line just separates, it's one of the vertices, it's one of the edges that separates each of the pentagons into 5 triangles. So it's at
the problem is that this
right
splits,
position.
You're splitting this pentagon here into
5.
This was an original pentagon. You're splitting it into 2 triangles here, and then you got some triangles down here.
Yeah,
let me show you my drawing.
Plus there's one that you cannot see.
Okay, look at this drawing right here. When I connect 1, 2, 3, 4, 5, it becomes the North Pole. And then when I connect 1, 2, 3, 4, 5, 180 degrees is 16, 17, 18, 19, 20. Those are the 2 pentagons, polar pentagons. And between those 2 polar pentagons is the equator. And Lee is holding up the equator triangles right there. They're only triangles across there. And that's what's showing right here, 6, 7, 8, 9, 10. If you were to take your icosahedron, Fred, and you numbered them and picked one side and said, okay, this is going to be my North Pole, and you numbered it 1, 2, 3, 4, 5, and you then went to the South Pole and numbered it 7, 12, 17, 18, 13, you would find that your equator is 16, 11, 6, 1, 2, 3, 8, 4, 19 thing. And then what I went ahead and did to prove the point is I went ahead and did exactly the way it should be done. What I argued was that this is the equator and that there should only be triangles around this equator. And so as I come down here, then I numbered everything. I took and I numbered everything out, and so I took my 3D icosahedron, I flattened it out completely into a 2-dimensional entity, and I would have a pentagon on top and a pentagon on the bottom. And then I took and numbered every entity. Here is 1, 2, 3, 4, 5 around here, and then here's 7, 12, 9, 11, 10 going around the outside. And then I went ahead and numbered the triangles that are on the polar pentagon. And there they are, 17 through 20. And if I come back up here, they don't match up. Oh, that's because let me see, that would be here, 17 through 20. That's it, 16 through 20. That's what they should be. So coming back down here, and then I took it and I took Joe's idea. I flattened them out. All that's left is the equator. The equator is what connects the two polar pentagons. That's all these figures here. And so then I went ahead and put the equator around it. I numbered it out. And so the South Pole has 16, 17, 18, 19, 20 that you can't see. And then it has these around it. So I'm totally satisfied that I did this correctly. And I'll be glad to send this to somebody. And you can, if you care to take the time to prove me wrong. And I'm going to ponder and double check all these. But I spent like 10 hours putting this together, trying to be fairly clear about what should be happening here. So, so anyway, these are all triangles around here.
Okay.
And I feel pretty good about this. I'll send it out. Anybody else want to? I hear Manu has his hand up.
Go back to the original diagram, the one you started with.
That guy right there?
Yeah. And what I'm looking at is where you've got, well, no, actually, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, no, okay, I'm okay here. I thought maybe there was a problem with the way you put the equator in there, but it's, yeah, it's like 11 connects to 16, like kind of line to line. And 8 connects to 1, 12 to 17, 7 to 2, and so forth. And so it does show that the two pentagons, north and south, all connect to a triangle in the middle.
Right. And I see what you're doing, Fred. If you'll number your icosahedron, you'll find that yeah, see, and what you're doing is you're sticking with the great circles, Fred. This is not about great circles.
No, this is about, that's not what I'm doing.
Okay, let me stop sharing so that you can see, and then we can.
What I'm doing here is it's only triangles. There is no pentagons unless you decide.
The pentagon's blue right there. It's facing me.
No, it's not a pentagon. It's a pentagon only when it's projected on a plane.
It's what?
It's only a pentagon when it's projected on a plane.
Exactly.
A pentagon is flat. So there's only triangles, surfaces that form this icosahedron. If you want to decide that, for instance, the blue that I made is a pentagon, then it's arbitrary. You decide that one, but you can choose anyone. You can decide.
Okay, but yeah, you can choose anyone.
Hold on. Hey, wait, there you go. I tell you, 3D is not for me. Even orienting something in the front of the camera. Okay, so now you can choose this one, but it's arbitrary. You can choose anyone at any vertex.
Yeah.
So when you say North Pole, South Pole, it does not exist. Anyone can be North Pole and anyone can be South Pole because of symmetry.
But once you pick it,
what we're talking here, if you remember on Wednesday, we talked about the dice, and we had different cycles that went to 1, 2, 3, 4, 5, 6, and 1, 3, 5, 4, 3, 2, or something like that on the dice. It's just a labeling problem.
Okay.
Yeah. But the other thing is
a labeling problem.
The other thing is that you can have the north-south pentagons, or you can have east-west. It's just that what's pictured as the pentagon, it has to be the same at the opposite end, at the other side.
So
Yes,
what
I
Richard
agree.
just said was,
I agree with that. But then the choice of equator, you have several choices of
no, you
equator
don't.
as well.
Once you pick the North Pole and the South Pole, which I
Okay,
agree,
once you pick
Fred.
the North Pole, but by symmetry,
No,
it's all the same.
No, wait.
Whether you pick
Once you
this one
pick
or
the
that
North
one,
Pole,
by symmetry, the reasoning is always the same.
okay, but once one picks the North Pole and South Pole, it becomes arbitrary. It's from outside the system because the system is all triangles. It's all triangles individually, and it's all pentagons anytime you choose a vertex. It's all triangles and it's all pentagons, depending on your perspective. But once you pick a North Pole and a South Pole, that's an arbitrary pick. And once you pick that, that pentagon that we're looking at right now goes to the top. If you would kindly put your thumb on the South Pole and a finger on the North Pole. You can use two hands if you want to. Okay, now hold it up so that it's North and South Pole, so that one of them's on the top and one of them's on the bottom.
Okay, like
Okay,
this.
but now hold it so that I can see the North Pole on the, there we go. Now bring that down. Now look, all there are is triangles on the equator. Now that
Yeah,
I've
we agree
chosen
with
my
that.
North Pole and South Pole, at the equator, there are all triangles. And
Yeah, we
that's my
agree with
point.
that.
What?
Okay, we
Good,
agree
that's
with
all
that.
my point is.
Okay, we
Good.
agree with that. But then you have uh, then you have uh, many different options to choose North and South Pole and to choose which
Absolutely
one is the
correct.
equator. And because of so you have many different options, and because of symmetry, it they're all equivalent, and it translates into a labeling problem like with the one we identified in on Wednesday.
I agree with all that.
Okay,
And
good.
you
So
agree with my point that once one chooses the
oh yeah,
North
yes,
Pole and
yes,
South Pole,
yes. Once you've identified one south and one north pole and put a mark on it, because otherwise you won't be
then
able
the
to
equator is all going to
identify.
be is going to be a great
Yes,
circle and it'll be all triangles. And I missed the whole point in the first place because it wasn't showing me an icosahedron. It was showing me the great circles relative to the icosahedron.
yes.
And I totally missed it. So in one hand, I'm just a stupid cluck. On the other hand, once I arbitrarily made a case and in my arbitrary case, what I'm saying is true. And generally speaking, what you're saying is true as well.
Yeah, we're in
Good.
agreement. Welcome to. I feel for you trying to deal with 3D. I completely understand your the struggle.
Okay, cool. And Manu has been very patient and kept his hand up. Go ahead, Manu. Share. When you're ready.
No. Okay.
Thank you.
This is an icosahedron. Now you remember the contour, the zigzag contour that we have around it. Here you are. If I pick any vertex of this, I can make past 5 of those. Are we in agreement? 1, 2, 3,
yeah,
4, 5.
Right.
Once I do that, watch me. You see this green band?
Sure.
Here it is.
Are you wrapping it on a pole?
That's my equator.
yeah.
Okay, good.
And that is the 6th circle of the icosahedron.
Right. And the equator only
And you
hits
see, this
triangles.
equator is only going through triangles that
That's right. That are what we call negative and positive. Amy said they're negative and positive.
yes. Here it is.
Perfect. There it is.
Okay,
Cool.
that's all I wanted to share. All right.
Good.
Thank you.
That was my point, and that is cool.
And then you get 5 plus 5 plus 10 is 20.
That's right. You get 5 plus 5, the pentagons, is 10. And then there's 10 around the equator. That makes 20. If you're arbitrarily going to pick a pole, that is the result. But if you're not picking a pole, And now I've got to look at the whole thing in terms of what is a great circle. And how come there are 6 great circles in an icosahedron?
Well, let me try this in terms of if you picked the east and west pentagons, then you would have a great circle in between them, which wouldn't be the equator.
That's right. It would be a great circle from North Pole to South Pole.
Yeah. So maybe that's part of the struggle of that. There's one circle that is going to be the equator, and that has to be between north and south. But if you take one of the other pentagons and match it to its opposite, then there'll be a great circle in between them.
Yeah. That's right.
Yeah,
there will be. And so, as we've said,
so maybe there's 6 great circles.
And as we've said, picking poles on an icosahedron is totally arbitrary. It's something that somebody outside the system comes in and says, I'm going to look at it this way, because that is not the way nature looks at it. Nature sees the great circles. And as we've been reading in this book, there are 31 great circle patterns. There are many great circle patterns, and what we've been discussing is the LCD, or the least common domain. What does LCD stand for? LCD stands for
least common denominator.
Least common denominator. Yeah, on page 239, just below figure 14.8. So, and I might as well share that because I think that's an important. Now we're getting right into the reading of the book, except that I am not. No, I am not prepared to get to that.
Please.
What's that?
Yes, I just wanted to add something here also.
Okay, please.
Okay, you remember this figure, this one that we've all done?
Mhm.
Yeah.
The expanded, the icosahedron with its dual. Yeah.
That's what? What is that?
The icosahedron is all the triangles expanded, and its dual is the rhombic dodecahedron that is here. The rhombic dodecahedron is that the composition, the figure that is composed, expanded of those pentagons.
Okay. Rhombic dodecahedron may be one of the names.
Do you see the icosahedron, the 20 faces of the icosahedron here? The triangles.
Yeah, but you've expanded
Accounted.
it. You've expanded it into a dual.
Yeah, there are 20.
The 20 triangles of the icosahedron are their number.
Yes, yes. Most expanded. That is single bond, each of them.
Yeah.
And when you do that, the space in between that conjugates with it to make a whole is the rhombic dodecahedron.
Yeah. So this is not an icosahedron. It's a rhombic dodecahedron.
That is a whole.
What?
That is a whole. Whole, W-H-O-L-E. That is a sphere.
Isn't an icosahedron a whole?
Now, I'm saying in this
is not a whole?
The icosahedron is completely folded into like this. It's a state like that one.
Okay.
That is stable.
Okay.
This state here is not stable. You have expanded the icosahedron, creating voids between, and those voids take the form of pentagons.
Okay, good.
Okay. And there are 12 pentagons. 1, 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5.
Well,
that is the dual. Yes,
there's actually 6. There's actually 6 because you have one on the pole as well. You have 1, 2, 3, 4, 5 around here. You have 5 around here, but there's one up here and there's one down here.
Yeah, that's why I say there are 12. 6.
Okay, good.
Good. I say there are 12.
Okay, good.
And the vertices of those, the centers of those form what you call the rhombic dodecahedron, which is a dual of the icosahedron.
Okay, cool.
Okay. Now, what is important here is that if you take any two of those vertices that are opposite, you can make pass a circle.
If I take any two of these or any two of the icosahedron?
Any two. If you take the rhombic dodecahedron, you take any two. Let's say that the first two are the poles. Then you can make pass 10 great circle joining opposite side of a rhombic dodecahedron.
Okay.
You make the same thing for the icosahedron. You can take pass 20. And the one that you chose, that is the equator, that is in there, is the 31st. You have 20 plus 10 plus 1.
Okay.
Do you see what I'm saying? If I take, for example, look at where my fingers are. I take this one, I can make pass a great circle here between my two fingers. If I make these two, I can make pass also, etc. So you can make pass 31st great circle at most in this figure. That's where the 31st came from. That's what I wanted to share. I hope that I haven't confused you guys.
No, everything that you're saying there makes sense.
Okay, thank you.
Now I'm going to get to where our reading is. And I think our reading is on page 246. Yeah, I'm way back here. As I read back through these chapters, there are a ton of great circles that are identified, and I'm just going to start with the figure 14.5, which is what I showed, which I thought originally was a dodecahedron or an icosahedron, and it's not. This is not an icosahedron. This is it's labeled as 4 great circle edges of the vector equilibrium. Now, this looks a lot like a cube octahedron, to me, anyway. But then as he kept going, and now we have 25 great circles of the vectorhedron, of the vector equilibrium, I'm sorry. And then we got the 6 great circles of the icosahedron. Then we've got the 31 great circles of the icosahedron. And then we get to our least common denominator conversation. Then we start splitting up the triangles of the icosahedron. Then we get to this intertransformability. And now we have the 10 to 14 lowest common denominator unit. And I'm not really understanding much of this because now we're talking about a vector equilibrium pattern. So I'm at least understanding that I don't understand. Then we have 31 great circles of the lowest common denominator. This blows me away. I don't know any practical value for the 31 great circles, but there they are. There's the rhombic triacontahedron, rhombic triacontahedron, the pentagonal dodecahedron, and the octahedron, and the vector equilibrium. So here's your rhombic triacontahedron, and then over here is your pentagonal dodecahedron, and here are all these great circles. And I'm sure this, I think, tells me why I don't understand anything, because these geometric figures can manifest many ways based on the great circles. And then here's 25 great circles. There's the rhombic dodecahedron that we were just talking about, A, and B is the octahedron. Very interesting. 25 great circle pattern revealed in the cube. This is a cube, and this is a tetrahedron. Wow. So great circles must mean a lot. Then we go through operational mathematics. We went through and we built our little bow ties last week. And we ended up looking at this cube octahedron with bow ties, and finally ended our reading on page, I thought I had it marked, but I don't, on page 246, which I think is right here. So I think we should be reading from conservation of angle, is where I do believe we should be reading. Actually, no. I have that we ended up here above this thing. So we have not read what has happened. We should probably have read that, but I think this is where we could start reading here, is just below this cube octahedron,
Yes.
spherical cube octahedron.
Yes.
Is everybody okay with that?
Yes.
Thank you for allowing me to warble around. I hope I've served faithfully, and if I've been confusing, I want to apologize.
I wanted
Manu,
to
you
show
have your
one
hand
more
up,
thing.
so go ahead. Yeah.
Yes. Do you see this? You say you didn't understand anything. Do you see this, huh? Do you know this guy?
Yeah.
What is it?
Well, it's a geodesic dome.
Exact. What is a geodesic dome?
You got me.
It is stable. It's the 31st great circles. The 31 great circles.
Okay.
That is it. You say you didn't understand what it is? This is the equator here.
Right.
And that is the dome. And you take the other one.
Right.
That
Gotcha.
is the first state that is stable inside the sphere. In the video that Fred sent, the guy talked about, well, what happened inside. This is what he was building. This is a multiple dimension that he was building inside.
Wow.
And that is what we have called the pi area. We've coined that word. The phi area. Phi area.
You should
This area,
type it and put it in the chat, if you would, please, when you're ready. Not right now. Don't stop what you're doing.
yes. Phi area, we've discussed that a lot here. We've talked about that word. It is that part of a boundary that we can calculate. This is a boundary.
Right.
And it's all triangles. We can integrate it. And this is the most expanded form of it.
Yeah. So
the other part, if you took actually a sphere completely, fine as you can, there will still be gaps.
Right.
Which is the convex part of it that guy showed as the stellar. He showed these little gaps. When you take the closely packed sphere,
yeah,
there is that stellation that goes out.
right.
And the more you are, the more it just elongates and goes away.
Yeah.
It is very, very convex.
Yeah.
That's what he was showing.
Cool.
And I don't know if I'm wrong in seeing a very practical application of this. Your homes should be this.
Yeah. His
Not
issue
the cube.
was he would have come up with that if he'd used triangles instead of squares when he did his two-dimensional projection of the sphere. He projected squares out there. And I thought, well, what if he used triangles on there? And you're talking about using triangles.
Yeah, but he did triangles. Because what derivative, that's what he was doing.
Oh, when he did his math, he was doing triangles. But when he did his
he was using triangles. Yes.
Yeah. But when he did his projection, he was in squares.
Triangular sectors.
Yeah.
Coming conically towards the center. That's what he was using.
Yeah, that is.
If you haven't watched that video, you have to watch it again.
Oh yeah.
Because a lot of things, and then it tells us about you don't need more than 3 derivations. You just need 2. You need 2 states before to know what is today.
Yeah.
That is, you need a second derivation.
Well, I noticed that in Fred's video is that he did these projections out. He was looking at squares, but as soon as he began to analyze them, he turned everything to triangles because that's how he came up with triangles, and that's how he did it. So
Yeah,
I'll have to look at it
because
again.
that's what you are really measuring.
Yeah,
You are measuring from inside.
yeah,
What is that volume that is in there that you can account for?
yeah,
Everything else we can't account for. So the best we can do is to go as fine as possible
yeah,
to limit what we cannot account for.
yeah.
Okay.
I noticed too that he went from one dimension, two dimensions, three dimensions. He got to the cube, and as soon as he built something in the cube, it was a sphere. It wasn't a cube. And I thought, oh, wow, that is weird. Uh, because a sphere is just a natural shape in space, where the cube was quite arbitrary, actually, if you think about it, because you have radii coming out and they're all different lengths. But if you stick with a sphere, all the radii are equal. And that gives you, go ahead.
And do you notice that we never count more than 5? Our maximum number is this 5 number. Once you went to dimension 7, you start decreasing. Actually, at dimension 6. Why? Because you take 2. We only know 2 and where we come from. We only know a bow tie.
Yeah.
We know 5 things. That's all.
Yeah.
1, 2, you measure. 1, 2, and then your origin.
Yeah.
It's 5. So when you go to 6, you are repeating. You just starting the same thing. Do you see what I mean? When you go to 6, you go to a sphere. You're restarting again. So the effectiveness of what you are counting, if you look at it from the point of view of efficiency of counting, is only those 2 that count. The first 2 pairs that form a tetrahedron. And then from that tetrahedron, that is half of it, you go into a cipher, and then you expand again.
Yeah.
So for our locality point of view, that's the most important. And you look at the way he represented it, it goes up. Yes, as you are measuring, the coefficient is going up. The constant, that is the volume, is going up. And then as soon as you hit 5 to 7, at 6, it starts diminishing. And the further you go, and then you can also feel that in terms of multiple dimension and folding. When I fold, I become smaller and smaller. That analogy of folding. This guy that was here, I'm doing this.
Yeah.
It is the same guy, but from my perception, it's just too small.
Yeah.
It's getting smaller. And you also go into, if you look at the whole universe as a continuum, the idea of folding and compressibility. And what I saw is that you can compress to a level and then it will collapse. It will collapse. And then starting, going, like if you take a ball and you press the ball, there's a volume inside. You press it, you press it, you press it. At a certain point, the pressing creates force that are centrifugal that overwhelm the boundary. And all of a sudden, your ball becomes flat because it had exploded. From compression, in an instant, you have, okay, yes.
Well, no, finish your statement.
I say from compression, you have gone all of a sudden to expansion.
Yeah.
And it is a phase of a continuum of universe, of energy flow.
Yeah.
Okay.
Can you when you say it goes to expansion, and in thinking of tensegrity, it sounds to me like it goes to tension. And tension is that's the other thing, I guess, in terms of if you stretch something out, it'll eventually break. And if you push in compression wise, it will collapse. And so you've got that compression tension working back and forth all the time in order to get what might be considered a stable equilibrium, but really isn't. It's still an equilibrium in motion. And it's what the chaos theory people would say. It's a far from equilibrium balance.
Cool. So Fred is waiting patiently. Manu, do you have anything to say to Richard about what he just said? Okay, then you should lower your hand if you're complete. Oh, you did. Okay, really cool. Wonderful, Richard. Fred, thank you for being patient, allowing Richard to do a point of information on what Manu said. Go ahead, Fred, please.
I have to watch this video again because I don't remember the video saying anything about tension and compression, saying anything about 1, 2, 3, 4 is essential and the rest doesn't count all that much. But thank you, Manu, for your contribution on that. But I don't remember the video saying anything about that. I watch it again. What I remember the video saying is that as dimensions increase, the number of dimensions increase, the inner volume decreases, and in the limit, that is, when you increase the number of dimensions to a very large number, in a limit, the only thing that matters is the surface, is the boundary. The inside does not exist anymore, is residual. It's epsilon, meaning a very small number. So the only thing is that matters is the boundary, is the surface. And this, it's not in the video, but I related immediately with what Steve always often mentions, is that black holes are two-dimensional, that all the information on the black hole is on the 2D surface of a black hole, and that the inside, you don't say that, but basically my interpretation is that if all the information is on the surface, the inside doesn't matter. So is it that black holes are so many dimensionals that they are related to what the video was explaining about higher dimensions and the surface being the only important thing? And then I related this to the holographic universe, where from 2D from information spread out in 2D on the surface, our multidimensional, I don't know how many dimensions, let's say 3, but it's probably more than that, is created as a hologram. That's something. I think, and that's a point I wish to make with Manu. I think it's important to distinguish what is being said in a video when or in a document when you use a document, and what is your interpretation of it. Make that distinction so that it's easier for us to be able to refer to the document given as something that exists, and take the other things as insights or speculation or opinions about what's been said. That's I think it's important. I'm done.
Cool. Really good. And I get to repent and read labels on graphics more, because that was not an icosahedron. It was the 6 great circles of an icosahedron. It sent me into a flurry of discovery that to me has been very valuable, but it was off the point of the graphic.
It's excellent. We all learned something about it. That was wonderful.
Yeah, very good. Okay, is everybody complete? All right, good. Let's head into our reading then. So I have down that we're actually gonna, we actually read down through here, and I don't want to go to the next page. So let's just say maybe we should, because it says, so what happened? What has happened? Well, we need to read to find out what has happened, I suppose. So let's start from here. We've made our bow ties now. Let's see what happens from here, if this is okay with everybody.
You need to start, I guess, the previous paragraph.
I
Yes,
need to
that's
do
it.
what?
Start there, making sure.
I need to what?
Start just where you are now, making
Good, I
sure.
will. Thank you very much. Making sure that all creases are sharp, unfold the paper to obtain a circle. In fact, I still have this thing on my desk. I have it. It's over here. Did I smash it to? Well, I'm sure it's here somewhere, but I don't find it. So unfold the paper to obtain a circle with three intersecting diameters clearly marked by folded lines, figure 1413. And I guess that's what this is right here. The circle is thus divided into 6 equal triangles. The process of sweeping out a circle with a compass ensures that all radii are equal. And because at one point in the procedure, all 6 pie slices are piled up together, we know that the central angles must all be exactly the same. 360 degrees divided among 6 equal segments yields 60-degree angles. First-hand experience has confirmed both the constant radius and 60-degree angles, and therefore the presence of an equilateral triangles with arc segments at their outer edges is experientially proved. One fold, line AB, faces you. The other 2 folds are facing away. Bringing point A to B, we create one of Fuller's bow ties. This is the bottom of 1413, right here. A bobby pin straddling the seam, and Fred was kind enough to show us a picture of some bobby pins last week. A bobby pin straddling the seam keeps the bow tie together. Two unit length regular tetrahedra joined by an edge. We repeat the procedure 3 times, producing 4 bow ties in all. It is then apparent that 2 of them can be placed seam to seam and pinned together with 2 more bobby pins to produce the tetrahedron, to produce 4 tetrahedra surrounding a 1/2 octahedral cavity. The other 2 bow ties are similarly paired, and finally the 2 pairs are connected along their congruent folded lines with 4 more bobby pins. A complete paper sphere emerges, figure 14.4. This strange procedure is created a very familiar pattern, 4 contiguous great circles, or a spherical vector equilibrium. The only materials required are 4 paper circles and 12 bobby pins. That is cool. I think there's magic in that language right there. 4 paper circles and 12 bobby pins. I'm thinking 12 degrees of freedom is what's ringing for me. And here's figure 14.4. This is our 4 bow ties created together. And dadgummit, I built 2 of them. I had them on my desk last week. And I just am not sure what happened to them. I guess they're forever gone. All right, what happened? 4 separate paper circles have been folded, bent, and transformed into bow ties and pinned together without paying any attention to converging angles. No special jig is required to line up adjacent bow ties and ensure that consecutive great circle arcs are collinear. Folded edges are simply brought together. 4 contiguous great circles magically reappear as if the original paper circles were still intact. Looking only at the finished model, it appears that we had to cleverly cut slits in paper circles in just the right places to allow the 4 circles to pass through each other. The procedure is reminiscent of the magic trick in which a handkerchief is cut into many pieces and thrown randomly into a hat only to reappear intact. Any comments or questions on that? Okay, I'll continue to read.
Yes, yes.
Okay, go ahead, Manu.
Do you see this? Do you see that?
Okay, hang on a second. You're showing us that, yeah.
Yeah, that's what she said. I just did the paper model. You see the 4 great circle? You have 1 here, you have 2 here, And then in the seam here, you have one, and then the second one there. You see that?
Yeah.
That's it. That's what, the two bow ties brought together.
Yeah, it's a double tetrahedron.
Yep.
It,
It's a stellar, it's the same thing as this guy.
Yeah.
Exactly the same with paper.
Yeah.
Okay.
it's not
So
the
sorry.
same as
What's that, Fred?
it's not the same. What Manu is showing, it's not the same shape
No, it's not
as
exactly the same shape.
1414.
Right.
No, because this thing is my folding. Normally it's like that. Huh? It's not straight it's not a straight line like this. Normally it's like
Right.
that.
Right.
But otherwise it's safe. I just use a scotch tape. It doesn't hold, doesn't keep. And if you make a mistake, you just amplify the mistake as you build.
Right. Okay. And let me see here. We have something in the chat. That was Fred. Collinear sharing on the same line. Okay, good. Thank you, Fred. All right. Who wants to read from here?
I'm okay to read.
Did I finish this guy?
If you can understand what I read with my accent, I'm okay to read. You tell me.
I'm happy to have you do that. Is this where we left off? Is this the next paragraph to read, or did I read that? I think this is next.
We start at a spherical vector equilibrium.
Yes, please.
Okay. A spherical vector equilibrium can be constructed through this simple folding exercise because of this specific interplay of its surface and central angles. Remarkable numerical operation is required to allow adjacent central angles to fold out of flat circular disks, while automatically generating correct surface angles. That four great circles will submit to this bow tie operation is not at all that four great circles will submit to this bow tie operation is not at all obvious from studying the whole pattern, and even less so in the case of other, far more complicated models.
Really cool. I would just like to say that I've been thrumming past my two bow ties. They were in the book as the bookmarker. That's where they were. I thought they were on the desk. They were in my book as my bookmarker. So good. We'll continue to read. Any comments or question on what Fred has read so far? Okay, we're changing topics here. Continue, Fred, if you like. And
Conservation of angle.
Okay.
Conservation of angle. Physics tells us that a beam of light directed toward the mirror at some angle from the left will bounce away from the mirror, making the same angle on the right. The angle of incidence is equal to the angle of refraction. Bucky points out that the same is true for the great circles models if we think of the path as trajectories. Yes?
Okay. Continue.
Great circles main... Oh, sorry?
Go ahead, continue.
I continue. Great circles maintain the illusion of being continuous bands, argues Bucky Fuller. However, the bow tie procedure reveals the truth about these patterns, and in so doing illustrates an aspect of energy event reality. A great circle path may look continuous, but what really happens is that as soon as a trajectory or great circle arc meets an obstacle in the form of another great circle event, they collide, and the course of both trajectories is necessarily altered. Both paths are formed to bounce back, just like a ball bouncing off a wall. Yes?
Okay.
Keep going. Here's the fun part. Because the intersection of two great circles provides two pairs of equal angles, their path mimics the classical collision in physics. The same angular situation results from two overlapping red circles as from an idealized energy event collision. These symmetrical patterns can therefore be thought of as a path taken by billiard balls on the surface of a spherical pool table. If you didn't see the collisions, you might think that two balls went through the same point at the same time. However, the true paths are bowties.
Wow.
This is quite an image.
Yeah. It's taking my breath away.
Okay, shall we stop and ponder a little
Anybody
bit
have
on
any
it?
questions or comments on it so far? Because it's pretty heavy duty.
That is the definition of a reflection. The incident angle and the reflected angle is the same.
Yeah.
And it
There is,
is,
let's go
and
ahead.
it's, yeah. There's what?
I say, go ahead, go ahead. I thought you had that.
Yes, and that is basically if you take a bow tie, you cut in the middle with a diagonal, like a great circle cut in it. That image is one V this way, and the other side of a mirror, you see the V at 180 degrees. So if you take the image in the mirror and the event in reality, that is, if you had a wall that was a mirror, and then you roll a ball at a certain angle to the wall, and it bounces off the wall, and then reflected over the mirror, you're going to see the inverted V. So the two V's are going to form wholly a bow tie. That is an analogy that she's bringing in.
Very cool.
Okay. Are you done, Manu?
You complete? Yeah, he's muted.
Yeah,
I'll tell you what I've got to do, Fred. Is I've got to go.
Yes.
I got to go buy some bobby pins and actually do this. I'm going to actually do this.
Yes, I think we should all do that and play with it a little bit and try to understand something. I'm going to share. It's a video, but basically it's an audio from Suskind about mirrors. It's a wonderful video that explains what we think of mirrors and what mirrors really do compared to what we think they do. And I've got to go back to this video several times because I listened to it once or twice already, and I'm not sure I fully understand. It says that what we see in a mirror, when we look at our face in the mirror, what we see is the opposite, like the zoom camera is showing us what we see in the mirror. But in reality, it's a cultural thing that we see us swept this way. We could as well be swept this way. And so I'm not sure I fully understand what he said, but I believe with regards to what we just read in the book, it's an interesting video to watch. I'll put the link in the comment section so that everybody can have it. And if you wish to, you can listen to it.
If you put it in the chat,
I found it fascinating.
It's not in the chat, Fred. Have you pushed send?
Not yet. Not yet. I have difficulties to
do we want to take time and watch it
and read at the same time. I'm sorry.
Do we want to take some time and watch it? Will it help us understand this thing, or is it just a side thing?
No, it's 15 minutes. Somebody's got to listen to it and ponder about it because it's not. It's all simple words, but it's quite complicated. I found it quite complicated to understand.
All right, very good. Thank you for adding that.
I'll put it in the chat.
Because we're about to engage in the fun part here, and I'm on the edge of my seat.
Yes.
So do you want to continue? Yeah.
Yeah.
Okay.
we've done the fun part already. You want me to repeat the fun part?
Oh, really? Okay, that's right. An angular event conclusion. That's right. The fun part. So he's explaining the hadron collider here and why everything is spherical. Cool.
Would you like me
But
to
when he says the
I can
surface of
reread
a
the fun part.
you can't believe what?
I can reread the fun part if you want.
Well, that's okay. It's you reminded me. I'm good. We'll go along with the imagination part next. Okay.
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 Imagine a great circle wall constructed vertically out from the surface of a sphere. If a ball traveling parallel to the sphere surface, describing another great circle, hit the wall and bounce back, hit the wall and bounce back. So imagine that. Imagine a great circle wall constructed vertically out from the surface of a sphere. If a ball traveling parallel to the sphere surface, describing another great circle, hit the wall and bounce back. Figure 15a. Maybe we should have a look at that. It's on
It's on the
next page.
next page.
Yes.
Do you want to do his quote? I
Okay.
can move ahead real quick. There we go.
Okay, I can read. I have my book, so you can look at the picture and I can read. Maybe it's helpful.
Okay.
It would bounce inwardly off that wall at the same angle that it would have traversed the great circle line had the wall not been there.
Ah.
It would bounce inwardly off that wall. Maybe you can show with your pointer there. Yes, that's one.
Bong. Bong.
That's what. At the same angle that it would have traversed the great circle line had the wall not been there. And we
Exactly.
have and the angles are
And
noted
the
there.
angles are equal.
Yes. And then I
Wonderful.
keep reading.
Yeah, please.
I keep reading. Adjacent, maybe you leave the graph there. Adjacent
Maybe.
bow ties, or maybe you go to the text, yes.
Okay.
Adjacent bow ties, therefore, produce collinear great circle arcs. Collinear means on the same line. Collinear great circle arcs, because the angle made by the paper disc bouncing back from a bobby pin collision point is the same angle the circle would have made on the other side if the bobby pin had not been there.
I've got to get some bobby pins. Go ahead.
Then Fuller continues, and it would bounce angularly off successively, and it would bounce angularly off successively encountered wall, so next after the one wall after the other, in a similar triangle manner. And that's
Wow.
same figure.
I'm just impressed here, if I may just say, it's triangles all the way down.
Yes.
I just thought I would say that.
I would like to reread that because I'm not sure it makes sense to me reading it.
Please.
Adjacent bow ties therefore produce collinear great circle arcs because the angle made by the paper disc bouncing back from a bobby pin collision point is the same angle the circle would have made on the other side if the bobby pin had not been there. Okay.
Okay, that's what this, whoops, that's what this line is right here. It's the same angle. If the wall's there or the bobby pin, because the bobby pin creates the wall. So it's the same angle.
Yes.
Yeah.
Yes. And on the next figure on the right, the B, you can see the bow tie pattern that's made with
yeah.
with a collision. And I don't know. It's speculative. Again, it's speculative what I'm going to say, but it triggers in my mind the idea of conservation law that we have talked about last Wednesday. We have this cycle and trajectory that remain that where the ball that is bouncing remains on and is not there's no going to another one. So it reminds me of the conservation law. If you guys remember that.
Wonderful.
Okay, I keep reading.
I was saying that
Hence, yes, go ahead.
if there's no friction, it's conserved, and the angle will be the same because
Yeah, but
energy is
okay,
conserved.
you're correct, but I'm not talking about energy conservation. I'm talking about conservation law. That is a value that stays conserved between different
Okay.
states in the cycle. But yeah, you're correct. If there's no friction, the movement doesn't stop. That is correct.
Okay.
Hence, I'm reading now. Hence, the completed bow ties. Hence, the completed bow ties. Sorry, that was in the middle of the. Fuller continues. Hence, the completed bow ties. The image of the colliding ball and great circles wall makes it easier to understand why Fuller interpreted great circles as the trajectories of energy events, and explains why he was convinced that these models have physical significance. His bow tie analogy is consistent with the classical collision model. And then we have this graphic that we have already watched of reflective bounces in local holding patterns in a figure 8 loop. In
And there's your bow
figure
tie.
A, the ball bounces back from the wall at the same angle it would have made with the wall on the other side had the wall not been there. So we observed that already. And in
Right.
B, the local pattern, the figure 8 loop. And
Right.
I think Manu is right. It's an energy conservation pattern in this sense. That's what Bucky says.
Yeah, and note that in action reaction, that's the way you represent the reaction. You know, if you take that figure 1415A, that is there. You know, if you consider that an incident force was where you have the first angle gamma there on the left side, the dash will be the reaction of it. And then if you compose the whole, you're going to have a parallelogram. Or, yeah, that's the way
Yeah.
you represent it in physics. But they never explain to students why it's like that. In that they say action like that, reaction like that.
Yeah.
Yes. And the resultant is a diagonal. Never explain.
Right.
It's just like that.
Yeah. Yeah. If I hear you right, they're saying this angle is the same as this angle, and it's just mathematically true. It doesn't explain that there's a boundary here that's explained in this diagram here.
It is actual fact a mirror effect. For everything to go full cycle, you need the concave, that is the real, the one that we see, and the convex, that is the hidden part. Again, the sine and the cosine.
Right
The
on.
cosine is the projection. It's projected onto a screen. That's what we watch as a movie. And the sine is hidden. But you take the cosine and the sine to make a full cycle. And
Okay.
that's the notion that in terms of practically we should always have when reading mathematically these things. The mathematical concept is to try to imagine things that we can feel that are in accordance with the mathematical logic that is being presented.
Right on. Okay. You want to continue, Fred?
No,
Well, and your hand is up too.
My hand is up. I'm a little bit puzzled by one thing here, is that Bucky in synergetics and Amy in trying to explain synergetics give us some insights about their thinking about how things could be. And that's an explanation of things. But the only real justification that this may be an interesting thing to pursue is that it looks like it makes sense. So it is. There's never going into the underlying and say, okay, now this came from that and that and that, and this is the reason why we get to this observation. And now this observation makes sense, but the underlying, what it's built on, is this. The underlying is never given, and this really irks me a little bit because everybody has an opinion, and everybody with a little bit of imagination can make it look good and make sense and all that. But why would that be true? Except the fact that it looks nice and maybe it makes sense.
I got you.
Okay, that's what I
It's a
wanted
good
to say.
poem. It's a good poem.
Richard, you got something to say about that?
Well, it just sort of connects with the Bohmian undivided whole approach that says it's really a perspective. Everything is a perspective depending on the angle in which one kind of looks at it. And there is, if you want, no absolute. There is no absolutely correct answer. Is what I'm getting out of rereading or reading more of Boehm's underlying sort of ontology about undivided wholeness. I don't know if that kind of connects with what you're getting at, but
yeah. It's but it's I've got a little story about that. You have a sociology background, am I right?
yes.
Okay, it's a little bit demeaning for sociologists, and it came from my genetics teacher. You allow me five to 10 minutes to explain this little story about that,
Yeah.
or
And then, yeah. And then we'll,
because that's a tangent. It's got nothing to do with what we're talking about here. Okay, it was in the 50s where people were digesting the eugenics of the 30s, and there was a lot of studies about the prison done in the prison populations. And they noticed that there was a disproportionate quantity, number, a disproportionate number of people that exhibited a phenotype. Phenotype is how they look, which was very tall, very aggressive in terms of behavior, and mostly a little bit stubborn people. And they found out that these people, the genes were super male. Super male is double the Y chromosome. Female is XX, male is XY, and super male, it's an anomaly, is a double, it's XYY. They've got double the number of chromosomes. And geneticists look at this, look at the prison population, and they said, well, look, those people, super male, are more aggressive, and that's why they commit more crimes. And and indeed, they were more aggressive, and they were more, the presence was more, in proportion, more important in the prison population than in the general population. And so geneticists found that they got the solution. They know exactly what's going on, and they were preparing a witch hunt for super males in order to remove, or maybe not remove them, but at least put them under observation in the general population. And sociologists came in, looked at the data, and said, no, 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 it's not the case at all. These people are not prone to commit crimes. It's because they're prone to get caught more often than the others. And that's where my genetics professor said, keep the sociologists away. Once they came in, nobody understands anything anymore.
yeah.
That's so that's the story about
Cool.
sociologists.
Well, that's a beautiful story in the sense of it reinforces um, the fragmentation side of divided
It
wholeness.
does. Yes,
And
it does.
and
It
when you
does.
take it back to that sort of time, it's when everybody believes sort of that separation.
Yes.
Yeah.
It,
Thank you.
it does absolutely. But I find it very interesting in this context. All right,
Very
I'm
good.
done
Thanks
with the
for
tangent.
Another little diversion. What do you see here?
a bow tie.
Exact. And how are these? You see a bow tie, no? And one is a mirror image of the other because it's a silhouette for you to see it as a bow tie. If I do this, it wouldn't be a bow tie to you. It would be some kind of bow tie that is not well tied.
Yeah.
And if you went to a wedding or something, that you're not
He'd
going
kick
to
you
be
out.
very well dressed.
Yeah.
It needs to be like this. Now, when it's like that, watch me. I'm holding this red in here. This guy here, this tetrahedron here, is exactly the mirror image of this blue one, the green and the blue, in relationship to the red axis. Do you see that?
Yes.
For you, and this is important, for you, the observer, to see it as a bow tie.
Okay.
This is to make the point that everything that we talk about is an ultimate interpretation. We interpret what is going on that we don't know. We interpret and then we agree. And our universe is a set of our agreements.
Yeah.
That's what it is.
Yeah.
And I think that fact is quite important. We should
but
always, yes, Richard?
well, again, I'm just going back to Bohm. I think he would say there were temporary agreements.
Exact. So we should never stop searching for what is interpreting what we are seeing.
Mm-hmm.
So we see this same thing, and this time we say it's a bow tie. But next time we see like this, it's the same thing. Hey, this become a boat.
Yeah.
Well, and that apparently is the flaw or the problem with Eurocentric science, or what often is referred to as Western science, that you get a certain amount of agreements and then it's sort of like it's now absolute and everything else is pushed aside. And so we have this problem of a particular perspective, if you want, with any number of agreements, I guess, concluding that this is the final answer. There's nothing beyond.
And coming to what we have with Steve, yes, this is an externality, but it's absolutely necessary. It's the tool of a Euler identity. I choose this guy here to be my referential. I choose it. Nobody else choose. Somebody could have chosen, as Fred was saying, this guy.
Yeah.
I choose this from external of a system. I choose to fix these two.
Right.
And I see everything in relationship to this origin, to this referential. Okay.
Good. And I think it's appropriate we have the time, if we just read the final paragraph in this section, we'll be able to start a new section the next time we read.
Okay. Can I keep going?
Yes, please.
Yes.
Okay. That we are consider the paper model. Am I right? Yes.
Did it say okay, go ahead.
Consider the paper model described above. Soon after an energy event meets its first collision, the new trajectory meets a second obstacle and its course is again altered. Conservation of angles determines the new heading once again. Conservation of angle determines the new heading once again. And the process repeats until, at the sixth collision, the great circle path comes back upon itself, completing the bow tie loop.
Wow.
That's 15B that we just looked at.
Please refer to what I've put on the in the chat box there, which I got from Fred's video in relation, and read it. And when you will be able to look at that, look at it in relationship to what we just said, the sixth.
I'm looking at the chat and I don't see anything. Oh, Manu,
I
graph.
put the graph there, a
Okay,
graph
good, thank you.
from the video. It is
Wonderful.
amazing. It is amazing.
Yes.
Well, I already saved
Shall we,
it to my computer.
shall we finish reading and go back to
Yeah,
that?
let's finish this read.
Yes.
Okay. Now open PDF. I lost my PDF. There you go. Okay, successive, you know where we are. Successive arc segment, last paragraph before foldable systems. Successive arc segments of one energy event form figure 8 loops, or local holding patterns, which both Manu and I referred to as conservation laws, which lie side by side and appear to be continuous great circles. Construction paper shows us how it works, and Fuller tells us that this is what happens in physical reality as well. Discrete energy events form local circuits just as discrete paper circles form bow ties. They only look continuous. Discrete means discontinuous.
Yeah. Okay, wonderful. Then next week when we start, we'll start here.
With foldable systems.
Yes. Yeah. And I'm very excited. So good. This is 228. All right. Maybe we should take a look at that graph.
Yes, I just got it from, I was taking notes.
Yeah. I think I saved it to my downloads.
I'm sharing it.
And here's the graph. I'll share it right now. Oh, there it is. It's being shared. Somebody shared it.
Yeah, I shared it already.
Good. And you like this graph?
Oh, yes. I'm saying very well that 5 is pivotal. You get to 6, you loop. Okay. And you can see it there. This is what the experiment, the guy was filling boxes and calculating the volume of a unit ball at each increasing dimensions. And that is, that is the formula that he has anyway. The recursive relationship and the recurrence relationship, and then the formula. Yes.
Very cool. Thank you for sharing. So Manu, how are you feeling and what are you taking away from tonight's call?
I feel robust. Do you hear me?
Yes.
Robust?
Yes, I feel cool and robust. I feel like I've grown, that there's some energy that has been added to my system.
You mean strong, robust,
yes.
Strong, sorry.
Yes.
Okay,
yes.
Thank you.
Yes. And then grateful. So that's what I take away. I think, to be truthful, that reading these 2 books on Wednesday and Thursday, I don't want to boast. I think that has improved my understanding of a bucket and in what context you can invoke it to guide. I think so.
Very
So
cool.
That's what I take away. Lee, you haven't said anything. How do you feel?
You should unmute.
What do you take away?
I got turned off at the very most important time when you, Manu, were explaining some very important things, and I was frantic trying to get on again. But I did it without help. Thank goodness. But yeah, thumbs up on it. I have been really excited about today, but a lot of confused. especially with the Fred, you sending that what is it? Not a diagram, the guy talking.
The video, yeah.
I could not understand any of it. I'm sitting there going, what is he talking about? I'm so confused. So, yes, I will have to go and study it again and then get clarification from any of you that get it next week, I hope. I enjoyed today. Thank you. Richard, how are you doing? And what is your takeaway?
You're muted, Richard.
Yeah, sorry about that. Had to step away for a minute. Yeah, I'm again, this is continues to reinforce my own sort of journey with Fuller's work, and in many ways, I find that I am most comfortable with understanding the tetrahedron and the concept of a minimum whole system, and how important that is to a kind of a foundational underpinning. And so it still is an exercise for me to um, expand beyond into some of these other sort of understandings, and that's what's so great about the dialogue that we have. Um, and for example, um, the the bow tie kind of configuration was very helpful for me several years ago when I was trying to take a minimum tetrahedron, like the three-dimensional one, lay it down flat so you see the two-dimensional version, which really is the four faces of the tetrahedron, and then multiply by dividing each of those triangles and get their minimum four. And then what I was trying to do is, in a kind of a three-dimensional way, try and take three of those next generation, if you want, of triangles, and reconfigure them in a kind of like a vertical contextual way, one set, two sets, and then the third set, and then take the fourth set and turn it into a methodology framework. In other words, a 1, 2, 3, 4, 5 step type of framework. Although what you get is a minimum of 3 or 4. You can expand it, but it can always fall back to the minimum. And so to really figure out a way to put the bow ties together in a way that they interacted with each other point to point, not edge to edge. And then the third one to connect with a point. And then you had them all interacting with each other. And then you had a pathway that comes off of one of them and a combination of two of them. And it's actually the flow through a process of helping or conversing or dialoguing. And so this is always continues to help me either refine that particular sort of modeling or be satisfied that at this moment, temporary, it looks like it's a model that can hold in the field that I'm associated with. Yeah, so I continue to take away that kind of learning from our discussions. Steve, how are you feeling? What's your takeaway? Having started off with the the proof of the experience that you were working your way through.
Well, I'm unmuted. Good. Thank you. I've got to go get some bobby pins. That's what I got to do. And I got to screw around with these guys more. What I love is the fact that we kind of came to consensus, at least everyone acknowledged that I can look at one thing different ways and be right from my point of view. And even though I may be right from my point of view, it may not be the way reality really is. I like there's something humbling about that, and I'm very excited about it. So it's been thank you guys for letting me share. Thanks for letting me run the meeting, work the knobs, and provide something here. I'm really convinced that this folding thing is I got to look into this more deeply because you know I from the Bucky point of view, dimensions are created by folding, and I've actually created an analogy about that, and I actually can take a piece of paper and fold and get to 3 dimensions just by folding, and that's exciting to me. But so I'm going to look at this folding a little bit more, and I've never used bobby pins. I think bobby pins are going to be my breakthrough. This one anyway, we made it through. We have a new topic to start on, and I'm looking forward to our next discussion. Thank you all for participating, and we'll see you soon.
Bye-bye.
Bye-bye.
I take away.